What are the learning outcomes? Students are at the end of the lesson, they will be able to appreciate the position of D and F block elements in the periodic table. You can go have a read through it. I'm not going to repeat it. Appreciate the use of electronic configuration of D and F block elements. So it becomes important that they know the general electronic configuration. CBSE has very, very clearly banned the use of logbooks. It's 3 years now. Then the logbooks are 4 years now. The logbooks are not being used. Earlier, logbook used to be very extensively used for electronic configuration. But unfortunately, even then, electronic configuration of D and F block was not very correct in the logbooks. Agree? Yes. So we'll be able to appreciate and use the electronic configuration of D and F block. What is that there to appreciate about electronic configuration? Teachers, I want your input. What is there that the child appreciate and use? In what way can the electronic configuration be used?
Know the stability. If they don't
Stability of oxidation states, stability of oxidation states, agree. Presence of color, magnetic behavior, agree?
Yes, ma'am.
Ability to act as oxidizing agents.
Ability to act as oxidizing, reducing agents.
Ability to form
one of you?
Ability to form coordination compound. How to
Correct.
form coordination?
Correct. In which oxidation state coordination compounds will be more stable? Very
Yes,
true.
ma'am.
Very
Yes.
correct. That's color. Color basically based on DD or FF transitions. Very correct. So
The students can predict the position of the elements in the
very
periodic
true.
table.
Very true. With the help of oxidation state, stable oxidation state, we in fact have a question like that in our exercise with lanthanoid. What predicting the position of that element in the periodic table. Very true, sir. Based on electronic configuration and based on oxidation state, which is based on electronic configuration also, we can predict so many things about the element. So teaching children how to use the electronic configuration will require them to write the electronic configuration first. Agree, all of us? Do we take care to make sure how to make them write electronic configurations? They are definitely need to know the general electronic configuration. And if they know the atomic number, because in board exam question paper, the atomic number alone will be given. Like there was this question in the board. I like that question. In fact, all the debug, I was just going through the question paper, which all of you are probably already done. Going through for this session, I found this very nice question, which is, in fact, like every child surely would have answered. There's no choice for it, thankfully, and good for it. Following ions of 3D transition series are given. They're given vanadium 3+, chromium 2+, Cu plus, Fe2. No, titanium was not given in this code at least. It was.
I think T codes, there were 3 sets of questions based.
Yes. So in this particular encode set 2, there was no titanium. There's vanadium, chromium, copper, and iron 2+. And they asked color, stability in aqueous medium, reducing property. So electronic configuration helps the child understand, decipher, or handle these questions better. So how do we teach? Like suppose we are talking about electronic configuration of an element in 3D series, because that's predominantly discussed in this chapter. Let's say scandium. Scandium, how do we teach? We either ask to write the inner noble gas configuration or just say argon configuration square bracket, say argon in square bracket and say
3D1 4s2.
Then we write, we say 3D1 4s2. We make sure the child fills in from 11th to 12th. What do we encourage them to fill in first after 3D, after argon configuration? It is the 4s or the 3D? Is it the 3D or the 4s?
4s.
We fill up 4s first.
4s.
And then 3D. And then the third electron goes into 3D always. And removal of electron also happens only from
3D first.
4s first.
removal happens from 4s, sir.
Okay, ma'am.
Right? When you add it to 4s first, and you remove it only from 4s. You don't remove it from 3D.
Always from the higher quantum level.
what happens is, this is where child also gets confused. In 11th, when the electronic configuration part in atomic structure, the last part is a little, we need to tend to rush up. What happens is we miss on how to write the electronic configuration of ions. When that is missed there, here also child misses. And once child starts removing the 3D first, that's when trouble becomes, because he or she will not be able to answer questions based on electronic configuration. So how to teach child, how to teach that, how to communicate. Addition is also from 4S and removal is also from 4S only. So that child needs to appreciate. That's the first part. That is the first thing that definitely the child should be able to do before proceeding further to the lesson. So we need to communicate that very, very clearly. Clearly that how to write electronic configuration of ions. 3D series, copper and chromium is a famous question. It's a famous question. There are so many questions which are based on the electronic configuration of chromium. Can anybody give a couple of questions? Because one of the methodologies of teaching D block is give them the answers and ask them to frame questions. It's one very interesting methodology which I always try. Give them the answers and ask them to frame at least 2 or 3 questions based on the answers. We can do it for P block also.
Madam, in 12th exam, they asked, madam, which is a colorless ion? Madam, titanium plus 4, I think. Am I right, madam?
Sir, in this code, set 2, I have vanadium 3+, chromium 2+, Cu+, and iron 2+. This is set 2.
In set 1, titanium was there.
In set 1, titanium was there.
Set
I have
1.
all the
Yes, ma'am.
3. I
4th
have.
question.
I don't. 1 second.
Yes, madam. 3 marks question.
3 marks question. Okay. Question number, sir.
4, ma'am. Section B
Yes.
code.
So that there it is clear, sir. But look at set 3. Have you looked at set 3 question and set 2? They've given vanadium 3+, chromium 2+, Cu+, and Fe 2+. They've
Yes,
given the
ma'am.
atomic numbers and they've asked identify the ion which is unstable in aqueous solution, a strong reducing agent in aqueous solution, colorless in aqueous solution. Give reason
Yes,
in each.
Got it.
In each. So this question
Yes,
can be
madam.
answered.
That question.
Correct. In this question, titanium is not there, sir. In set 2, in set 1, it is there. In set 2, it is not there. So at least the questions, these type of questions are better answered if the child has clarity on electronic configuration of ions. So it becomes very important for us to make sure child knows how to write the electronic configuration of the ions. Correct? Let's go
Okay.
on to, yes, let's take up.
Yes, ma'am. Yes.
Students will be able to appreciate another learning outcome, very, very important. I feel is the soul of the lesson, according to me. Okay, I always believe that every lesson, I personally identify soul, meaning the core, the important aspect of a lesson. I would say, according to me, this is very relative. It's to me personally, is appreciate the relative stability of oxidation states in terms of electrode potential values and electronic configurations as well. So if you take out the electronic you check out the oxidation states discussion in our textbook, NCERT textbook, we just have a half a page discussion. Remember, below a tabular column, there's just half a page discussion about oxidation states of 3D series, basically, and also transition metals. In that, we have these following. Why transition metals show variable oxidation states? That's one very important aspect. Why there are more number of oxidation states in the middle of the block? That's one. And unlike the non-transition metals or the elements groups, we find heavier elements preferring the opposite of inert pair effect. That's one concept that's discussed in the paragraph, a chota sa paragraph, very small paragraph, where all these points are put in with examples. And the last line is about that mention of the possibility of synergy bonding, where they say carbon monoxide is able to stabilize a metal in its zero oxidation states. So these points are put up in a small part a small paragraph in the textbook. So it becomes and many questions, like you yourself gave me, what are the questions which can be based on oxidation, stability of oxidation states. Many questions can be asked. I'm sure all of you will understand which part of the textbook, because I have an older edition of the textbook. I don't have the new edition of the textbook. I'd say under which tabular column I would make it more clear. It's under tabular column 8.3, oxidation states of the first row transition metals. So yeah, there's one more point I missed out. Lesser number of oxidation states at the extremes. This is another very important aspect that is being discussed under oxidation states. What are the points? One is more number of oxidation states exhibited by transition metals. Second point is middle of the series, more number of oxidation states. Third point is at the extremes, less number of oxidation states, and heavier elements, especially they have taken group 6 and discussed about tungsten, showing preferring higher oxidation state when compared to chromium, which is opposite to the general trend we see in P block. And the last paragraph, small paragraph, lower oxidation states are found when complex compounds with ligands capable of pi acceptor character in addition to sigma bonding. They've given the examples and showed that nickel and iron in their carbonyls exhibit zero oxidation states. So this small, I'd say approximately half a page, a little more than half a page under tabular column 8.3 is very, very important. And how do we take on these? And the child should have definitely clarity when he passes, when he's out of this lesson, when he's finished this lesson, he should be able to answer all these questions based on, anybody would like to talk about more number of oxidation states? Let's very quickly recall what we understand about extremities. We have the tabular column. I don't think I have it with me. I just quickly run through. Yes, I have it here. So points are more number of oxidation states. What do we say for that? What do we tell children? Why transition metal exhibits more oxidation state? In fact, there's one question in the board exam. How does the oxidation state variability differ from non-transition metals? Tin and lead, and when you compare it to transition metals. This is a very famous question. It's also there in our textbook. How are the oxidation states different in transition and non-transition metals?
In transition elements, they differ by unity, ma'am. In non-transition elements, they differ by 2.
Correct. So that's a difference. Why so many by transition metals? How do we explain that to children?
The similarity in the energy states of
N-1, N-1D and NS similarities, and we need to understand that when we say +7 oxidation state, are we very clear what we mean by +7 oxidation state?
Presence of unpaired electrons, more the number of unpaired electrons in the NS orbitals.
Yes, ma'am.
When
So
we
we are
say
talking about the
+7,
possibility of sharing of those electrons.
when we
Not
say
just,
+7,
yes,
we shouldn't know the child always thinks of losing
correct.
the element
Yeah.
capable of losing, so that we should clearly communicate
Yes.
that
Only
not more
sharing.
than 3 electrons can be lost by an element.
Correct. That's when Sindhu ma'am said more number of electrons in the d orbitals also could result in sharing. So the possibility of +7 exists only when there is a possibility of sharing. So when there are so many questions that are based on this, they will say manganese, oxygen is able to. This is a P block question also as well.
As you
Oxygen
say,
is
ma'am,
able to-
yeah, oxygen and fluorine only stabilize the higher oxidation
Yes,
state. So
yes.
that point has to come in.
Yes, that apart from that, there's one thing that captures a child's attention immediately is manganese oxide is Mn2O7, the highest oxide, whereas the highest fluoride of manganese is MnF4. So this captures a child's attention because he closely follows that the most strong, most powerful oxidizing agent is fluorine. Yet oxygen is able to oxidize manganese to its higher oxidation states. That is something which triggers this kind of, attention towards when we can relate that though weaker in some ways, there is something which is additional. You can bring in, personality traits of people here and talk about just having a power is not enough, but then having an extra skill, how it helps in case of oxygen. So this kind of relating to, day to a person's personality also can be done here. That's one way children catch on these aspects very, very quickly. So coming back to this, more number of oxidation states, apart from the fact that the energy difference between N-1D and Ns is less, so the ability to lose and also share electrons are possible, resulting in more. What about less, that is something like less oxidation states in the extremes? We say less number of electrons to lose and less orbitals available also. How do we explain
Unpaired
the
electrons?
Less number of
More.
unpaired electrons.
less number of unpaired electrons, less number of electrons to lose?
Yeah.
So extremities also can be explained. How do you explain that manganese having larger number? Why is it more in the middle?
Maximum number of unpaired electrons in the D.
Chromium has the maximum
Chromium,
number of, chromium has the maximum number of unpaired electrons, but
But manganese will be able to form a double bond also.
yes, the ability of manganese to form covalent bonds with oxygen, which being not just an oxidizing agent. Now, there's always this dilemma, do we use oxidizing property or electronegativity here? Definitely, we don't use electronegativity. Please, correct me if I'm wrong. We don't mention electronegativity at this context at all, because children end up writing oxygen, fluorine, electronegativity. They say fluorine is more electronegative. We don't talk about electronegativity. Talk only about oxidizing power. So when we talk about extremes, we say less number of electrons, less number of unpaired electrons. So the oxidation states are. So this is the third point. And talking about why group 6 we have this trend of chromium able to tungsten able to show higher oxidation states, stabilize in higher oxidation states. Anybody thought about that? Chromium 6 in group 6, molybdenum 6 and tungsten 6 are found to be more stable than chromium 6. We know chromium 6 is a strong
Oxidizing.
oxidizing agent. So it's not stable. So how do you explain the stability of +6 oxidation state for tungsten in group 6? It's not mentioned.
As we move down, the lanthanoid contraction prevails.
Correct. Yes.
And so the tendency to shrink and possess a high positive charge density.
Yes,
Tungsten
ma'am.
with a positive +6 charge experiences a high positive charge density.
So when we say the possibility of high, so the sharing is more effective. Is that what you're suggesting here? Because it happens only with
Yes.
oxide. It's only with
Yes.
oxygen. So the sharing becomes more positive. That's right, ma'am. That's exactly what all of us have understood. So when we talk, when child is going to be really intrigued at a point here where it becomes our duty to tell the child, unlike when we say in group 13 or group 14, where we say as we go down the group, lower oxidation states are preferred over higher oxidation states. There we bring in the concept of the shielding factor, the inert pair effect. Here we talk about the possibility of because of the lanthanoid contraction. So can we say this is one of the consequences of lanthanoid contraction? Apart from the consequences.
Also, I feel with a +6 charge, tungsten is highly hydrated compared to chromium.
Correct. Very, very highly
That is,
hydrated.
yeah.
So it's more stable because of its
Hydration.
medium. Yes. So this is another point. This paragraph has such a, in fact, it takes at least 1 period, 2 periods to complete just this half a paragraph in the class because there's so many things which are not said explicitly in the textbook at all. And the last point which I wanted to talk about, low oxidation states are found when complex compounds has ligand capable acceptor. This is again talking about synergy bonding here itself, the ability of carbon monoxide and the metal to involve in sigma and pi bonds. resulting in stable bonds. Again, I have a very unusual way of talking about covalent. Unusual means I think it is. It reaches out to students also better. I tell them this. I show them like this. This is a covalent bond, more like this, and this is a coordinate covalent bond, something like this. And I show them this is an example of a synergy bond. A coordinate covalent bond is this, and a synergy bond is relatively more stable, talking about the stabilities. So this particular aspect in the learning outcome, the child able to relate and appreciate oxidation, stabilities of oxidation states to begin with, and how do they relate it to electrode potential a little later when we go on to the tabular column, and interpret data and analyze the results of the interpretation that comes with the analysis of the tabular column, learns the various steps. This basically talks about the preparation, methods of preparation of potassium dichromate and potassium permanganate. Again, if we can do it in a differentiated, like do the same thing, the potassium permanganate in part of the board and dichromate in other part, and compare the steps, it becomes more effective, and we save time also when we do them together. I do it always together, so that they learn. And another technique I use is like the products can be predicted, but they need a little experience to do that. Anyway, they are going to learn by heart some byproducts. Ask them to learn by heart one stoichiometric coefficient and back balance, instead of sitting there and trying to balance by trial and error method or oxidation number method. When you remember one stoichiometric coefficient and learn the equation, anyway you're learning the products, when you know the reactants, learn it and then back balance. That is time saving. Children are able to do it better. In fact, they do it so well in the examinations. So you can try that technique of making them learn the equation. So in this part, it's this last two part, express properties, everything is about equation. Then one silver lining about this lesson is that is the only part where we have more of equations, the dichromate and permanganate, preparation and properties. So by teaching it, by placing them together, divide the board into two, and preparation of permanganate, potassium dichromate, it can be done. Wonderful. And we can also do it in the, we can take them to the lab and do simple activities based on that. And properties also. Properties, they already know permanganate. When they're doing titration, they already know some of the reactions. About permanganate, sometimes it is very exasperating for children is predicting the products in the basic medium. So unless their redox chapter that is thorough and they know the number of electron transfer in acidic medium and basic medium, they will not be able to predict the product. Am I correct? When the question says permanganate reacts with iodide, unless the medium is mentioned, it becomes a challenge for them to predict the product. In the board exam, I don't remember, teachers, can you tell me, do they give the medium?
Yes, ma'am, or either they give it as completion of equation.
No, completion of equation only they give, ma'am. In 12th, they only say complete the following.
LHS will be given. Yeah.
H plus or H2O. They would write.
They would give.
So that way we'll get an idea.
Correct. That way only they can get an idea.
But otherwise, sometimes it used to be a statement question where they write the equation in acidic medium that way.
That way. Somewhere, unless the child has some inkling of how, what is the medium, it is very difficult. So here, purely teaching redox balancing is better idea than asking them to learn by heart. Teaching them the technique, either oxidation number method or ion electron method, if they missed it in class 11, here it becomes very important, because this whole part expressing properties, child is able to express properties, that outcome happens only if the child is able to translate it into equations, because that part is only about equations. And apart from that, we have structures of only a couple of structures, the permanganate and dichromate. So we also have some characteristics in the characteristics of D block elements, and then the this is general outcomes for the lesson itself. We'll
Another thing which, ma'am, I would like to say is,
please, ma'am,
when we teach the redox lesson, the method which we teach first, that's well understood. By the time we teach the second method, they get confused.
Ma'am,
And
this is
I
something,
feel-
yeah.
Yeah, I feel the oxidation number method is the quickest way to balance the redox reactions. So if you take up the oxidation number method first, then the child will take up the balancing in not only in this lesson, also in many of the P block equations, there are redox reactions. So quickly they learn to balance. If we can bring the oxidation number method first, that would greatly help the children. What do you feel, teachers?
I do
Thank you,
feel the
Lakshmi.
same. Yes, I do start with oxidation number. Just
Yeah.
once it clicks, it's just 2-3 steps. They do it off. Just 2 steps.
Yeah.
Ma'am, I kind of do it a little differently, ma'am. What I understood is oxidation, I go with half reaction method, ma'am. I don't go with oxidation number method. For one, it's a little lengthy. So like Lakshmi ma'am said, once they learn the first method, easier method, they will not think about the
Second method, yeah.
yes. So I teach the lengthier method first. For one, they get clarity, they get a lot of understanding of how electrons are being transferred instead of putting it in a single, and their work is a little messy in 11th standard. They write the lost number of electron lost on the arrowhead itself, cut it and write the number, then multiply the coefficients, and then rewrite on that. It becomes a little, this is my experience. And like I said, it's what works for us is the right method. There is no right or wrong method in that. I prefer the half reaction method all times. In fact, I say even in 12th, you put it up in the rough side so that you get clarity on balancing. So each one has our own kind of way of putting it across. Yes, one method. Thoroughness with that method stays. Oxidation number method is quicker if the child is neat and it's not confused over her or his or handwriting. Ion electron, the upside of it is whatever mistake we make is clearly seen. We can easily identify where we went wrong when we separate them and try to balance them. So any method you take, please make sure the child is thorough with at least one pakka. Not insisting on doing both, being thorough with one. So anybody has any other inputs, experiences with regarding to oxidation number method? Because this last part of the chapter is best learned by teaching them the technique and not encouraging them to learn by heart. And in this lesson, correct me if I'm wrong, there are 2 disproportionation reactions. Am I right? That's another way of encouraging them to, towards, they like disproportionation reactions. There are 2 disproportionation reactions. One is in the preparation of permanganate, the second step of preparation of permanganate, and the other one is the one very famous one we just discussed. So anybody has any other thoughts on equation, communication of equation? Teaching them how to write ionic equations. And also, I'm sure all of us agree, it's better to teach them to familiarize themselves with ionic equations rather than complete equations. What is the disadvantage of writing complete equations? They're not wrong.
Too many byproducts.
Too many, yes. The ones which are not undergoing any change can be removed from the scene at all completely to fasten the process of balancing itself. So these are some techniques that we need to tell, which is not there in the textbook, which is not there in any, you search the Google, you are not going to get these techniques. We as teachers play a very important role. And it's very, very important that we write and balance the equation on the board and not bring a chart and hang it there. Or write the equations on the board and then keep it. No, it's okay if we make mistakes. In fact, it's better we make mistakes. We will make mistakes. We are humans. We will tend to make. It's better when we make a mistake, when the child notices, oh, ma'am, point out, ma'am, I think this is not balancing. We move back from the board and look at it. That's a very important communication to the child. It's okay to make a mistake. And it's absolutely fine to correct it. So I recommend that all of us write equations on the board and not carry a paper with us and copy, or have the textbook with us and copy equations. Very bad idea. It will hardly take 2 minutes for us, because we just feel that if we make mistake, what happens to our image in front of the student? It's absolutely fine. When we accept that, yeah, I can make a mistake, no problem. Child understands that, okay, I can also make that and correct it once I identify it. So that kind of generosity to ourselves we need to give. So that's basic learning outcomes, which is very close to what is there in the textbook. I'd like to go a little fast. We have already discussed this, the key points, trends, reasons. Key points are very less in this chapter. Methodology, recall, prompting to predict trends. Again, there are so many ways that you could do it. Especially trends and give reasons can be discussed by asking them to recall P block, because we normally do this lesson after P block. And P block is all about trends and what are the reasons behind it, and asking questions related to previous concepts. Use data given. This is very important. There are a lot of data given in the textbook, which we are going to discuss the next half an hour. Interrelate the trends and properties. Use Blackboard to write equations. Like I said earlier, it's very, very important methodology. Very important. Now, some of us feel it's like I have the slides, it's online, and I've got so many tools, but nothing like us writing on the board, especially equations and numericals. Working on the board with the students in their notebook and us on writing on the board works the best. It's the best way to come teach chemistry. Manufacturing methods, maybe yes. There are some, colorful charts we can use it, and differentiation is one methodology. Now, this is what I am really interested in. This is where our actual discussions begin. Now, these are data interpretation graphs. Let's discuss these graphs. Teaching child to interpret the graph, identify anomalies. Let's first ourselves predict the anomalies, or what is that unusual thing that we notice in this graph. This is again picked up from the NCERT only. This comes under melting point. Under physical properties and the melting points, this is discussed. Very, very prominently, chromium in 3D series, chromium having the highest melting point. Manganese having, there is a dip. There is a dip. And when we go to the 3D, 4D series and 5D series, when we see tungsten has higher melting point. So a little unusual. That is an anomaly. Again, when we talk about molybdenum, and then a decrease to TC, and then there is an increase to ruthenium. How do we explain these anomalies? They're not the same. They're not the same. For chromium and manganese, I'm sure we clearly know what is the reason for chromium having higher melting point, because stronger metal-metal bonding. Stronger metal-metal bonding because greater number of unpaired electrons. Am I right? Am I missing out any point here?
Yes, ma'am. And the same thing happens now, but manganese also having 5 unpaired electrons, but there's a tip. So that's where the anomaly comes in.
That is where the anomaly is.
Yes.
In 3D series. Any inputs for that? Why manganese has, though chromium and manganese difference is, chromium has 6 unpaired electron, manganese has 5. So it's only 1 electron, which is less in manganese, unpaired electrons. But yet manganese melting point is so much lesser than that of chromium. Any inputs there? But again, this is not discussed in our textbook. It's not there in our NCERT. How do you explain this to the child? Okay, we'll come to that later. Let's take the extremities. The melting points are decreasing because the metal-metal bondings are less number of unpaired electrons. Understandable. What about tungsten? Hafnium, tantalum, tungsten, rhenium, osmium, iridium. There is a particular trend there. There's nothing like it's increasing, becoming highest, and then decreasing. It's the 3D and the 4D, which is a little intriguing with manganese, and the TC, where we have dip in melting point.
Middle group elements are having a dip, though not very prominent in the case of the 5D series.
Yes.
Talk about the extra nuclear attraction of the fire, no?
Stable. Yes, ma'am. Extra nuclear attraction. That means the metal-metal bonding in manganese is not strong. Yeah, it is not strong because the electronic configuration of manganese is argon 4s2 3d5. Am I right? And the 5 is a half-filled state. 5 is a half-filled state.
It's an unusual stability of electronic configuration.
That's how.
the symmetrical electron cloud is prevented from being participating in the metallic bonding.
Correct. We could say the I would use the word diffused. There is the electrons are not so diffused. They are
Not
like
so diffused.
not so diffused. So the number of electrons which are contribute towards metal bonding is less. And that becomes number of electrons contributing towards metal bonding becomes less. Definitely metallic bond becomes weaker and then melting point becomes less. So this is one point we definitely need to tell, because this is not there in the textbook. Unless we are clear, we cannot explain this to students. Chromium, all of us do it very well. At the end also, copper, we do very well. We speak about it. But it's only this manganese and chromium that we are little kind of, not able. Chromium we do, manganese we don't. Tungsten, what about tungsten? Having very high, though along the same
Again, diffused electron cloud and hence able to participate in metallic
diffusion
bonding.
is more, yes. Diffusion is more, greater metal bonding, stronger the metal bonding, greater is the melting point. It could be related to atomization enthalpy, ma'am.
Yes.
We can also
Enthalpy
say,
of atomization also will be
The
higher.
trends are
Very
Follows
good.
the same similar graph structure.
yes, we'll have the similar graph structure, but atomization enthalpy being higher is not the answer for higher melting point. Let's all be very clear about it. Mentioning about atomization enthalpy is not going to reflect on melting point. Melting point is best explained only by the metal bonding and the number of electrons that are involved in metal bonding. So that's one graph, and I think all of us are good with that graph to some extent. Let's take up the Gudgeson graph, the graph trend in atomic radii. This is also very, very important, very lovely graph. So many things which are said there. Let's quickly look at the graph showing the 3D, 4D and the 5D series. Let's take the 3D series. What is that we notice? Size. Again, this is picked up from the NCERT only. What is happening to the size? How do we explain that zinc's size is increasing, correct?
Yes.
Whereas in the P block, when we say across the horizontal, when we say across the period, the size decreases.
The electrons added are in D subshell, which are more less penetrated and hence more diffuse.
Yes, they're less penetrating power, hence more diffuse. So the effective nuclear charge experienced by those electrons are less. So the atomic size increases. Am I right, Lakshmi ma'am, in elaborating what you just said?
Yes, yes, yes.
So it becomes important. And again, this particular part about zinc being larger in size than copper is not mentioned in the textbook, but it is given as a data. So data interpretation is very, very important, especially from the graph or from the tabular column. If you see the 4D and the 5D series, is not much. It's the same kind of swing kind of graph, but then it's very, very drastically seen between copper and zinc. So here, I think all of us are very clear how to interpret this, how children also do it very well. They don't have any problem with this graph. Only the melting point graph is a problem for them sometimes. This is one of my favorite tabular columns. So we can spend 1 to 2 periods in this tabular column. Agree?
Lot of data interpretation from this one. Yes, ma'am.
Ma'am, you're saying something? I didn't quite catch you.
No, a lot of data interpretation, just looking at this, no? From this data.
Lot of the data interpretation. So what are the data that we normally interpret? So anybody can, not having much interaction at all, said will I'm ending up talking, Lakshmi ma'am and Sindhu ma'am punctuating in between. Others also, please do share your thoughts. We're looking forward to it. It's not necessary that our perspective is the only perspectives. We are hoping to get more perspectives. In fact, we have this, I am sure Sindhu ma'am and Lakshmi ma'am will agree. We used to have this wonderful scoring key discussions. It's only that it used to be scheduled for half a day and we would want to rush after that. We had many enlightening educative sessions where we used to discuss the question paper and elaborately the answers that children can give. Most of our learning happened there. I am sure ladies, Lakshmi ma'am and Sindhu ma'am will agree to it.
Yes, very much, ma'am.
Yeah, we owe to our seniors, teachers who were there with us, who gave us lot of input, and it's from them that we learned also, apart from our peer group now. So it comes with sharing. It comes with sharing ideas and perspectives. So I request teachers to please tell us how you interpret this. What are the data that you use from this Tableau column?
Madam, these values need to memorize by the students.
No, sir. No, sir. The data should never be memorized by a student. You should not ask them to memorize data. We should teach them how to interpret data, sir. How do we interpret the data? What do they see? Like first ionization enthalpy of atomization. What is the trend? What do they see? And how do they account for it? So those are the things that we need to teach them, sir. Not ask them to learn data, E naught values, no, densities. You don't ask them, just ask them how to interpret. They'll do it beautifully, sir. They'll ask you, in fact, they'll provoke thoughts in you. They will trigger questions in your mind as to looking at the first ionization enthalpy, which I think Lakshmi ma'am mentioned about irregularity in ionization enthalpy part yesterday. We should discuss about it. This was a paragraph in our textbook, which is forever remaining a mystery, which says about reorganizational energy, which is all about this ionization enthalpy, first ionization enthalpy, irregular values of first ionization enthalpy. So we'd like to hear from you. How do you explain the irregularity in ionization enthalpy? It's not of much significance. There is, you see, there is increasing ionization enthalpy. In between, ionization enthalpy across the period will increase. Agree? This another anomaly, if you see size-wise, zinc is larger than copper. But look at the first ionization enthalpy of zinc. It's higher than the first ionization enthalpy of copper. I'm sure all of you would have noticed this.
Yes, ma'am.
Yes, ma'am.
Yes, we just saw a
Yes,
graph
ma'am.
where we saw atomic radii of zinc is atomic radii, yeah, larger than copper. But when we look at the ionization enthalpy, and we know how atomic radii and ionization enthalpy are related to each other. So how do we explain this to a child? So when we say a smaller size, greater is the ionization enthalpy, correct?
Yes, ma'am.
Yes, ma'am.
But zinc has larger size than copper, but its ionization enthalpy is unusually higher. That's one thing child is definitely going to ask us. And there is no steady trend in ionization enthalpy when we move from the left to the right side. When we see ionization enthalpy seems to be overall from a bird's eye view seem to be increasing, but then there is a dip also. You say nickel, there is a small decrease, then it increases again, and manganese to iron there is an increase, iron to cobalt there is a decrease. So there are irregularities. You talk about titanium and vanadium, you see a small decrease. So this is a very textbook has said something about organizational energy, reorganization energy. What is our take on that? I'm sure all of us will agree the relative energy of atomic orbital is not fixed as we start ionizing an atom. Correct. The relative energy of atomic orbital is not fixed as we start ionizing an atom. So when we start removing an electron, we said in the beginning itself, we established when we say electronic configuration of ions, we said we remove electrons from 4s first. When we do remove electrons from 4s, and there is, like say for vanadium, there is already the electronic configuration of vanadium would be there in the front of us. 3d3 4s2, argon 3d3 4s2. So when we remove one electron from vanadium, say for vanadium I take out an electron, there is one electron remaining in 4s. So the vanadium ion plus ion has electronic configuration 3d3, 4s2. And we have already established the energy difference between 3d and 4s. That is n minus 1d, and 4s is not much. Energy difference is not much. So could we have the possibility of an electron transferring from 4s to 3d?
Yes.
Yes. So we are talking about that transfer of electron from 4s to 3d, where there is a reorganization of electron resulting in reorganization energy, which adds on to the ionization energy, enthalpy, resulting in a variation in trends. But whereas in chromium, no such thing happens. Why in chromium no such thing happens? Because in chromium, it's completely half filled. 3d and 4s are completely, so not much of remarkable change happens there. Let's take up this particular aspect of, so that reorganization enthalpy adding on exchange energy, adding on to ionization enthalpy results in the irregularity in ionization enthalpy first of 3D series. How do we explain copper and zinc? How do we explain copper and zinc? We can just quickly do, we're like kind of 15 minutes more, we do a couple of points more.
Zinc, it's a fully filled 4s.
Yes, ma'am.
So removal of an electron disturbs the stable configuration.
Correct. So here also we talk about stability of the electronic configuration. Stable electronic configuration, though the size is larger, disturbing a stable electronic configuration requires more energy. Hence, higher ionization enthalpy. Are we all good with this?
Yes, ma'am.
Yes. A second, third ionization enthalpy we don't have. I think it's self-explanatory, and we'll take up next atomic ionic radii we have seen. I want all of us to look at the standard electrode potentials. Standard electrode potentials and density, small variation. Again, density increases. We know density increases. Sir has pointed out, somebody has pointed out an arrowhead towards 3+ radii of scandium.
Yeah, by mistake it came, madam.
No problem, sir. So let's look at standard electrode potentials. This we have already touched on it. The only element which has positive, only metal which has positive E0 value is copper. What is another little unusual that we notice here in the standard electrode potentials?
Manganese.
Manganese. Yes, ma'am. Manganese is
Unusually negative value.
Yes, ma'am. There was this board question, no, this year, based on which is a stronger reducing agent. Am I right?
Yes, ma'am.
This also was a question. E0 of value for copper is positive was also a question. And that was in set 1. This was a question. I think in set 2 we have a question. Yes, here the ions are different. There's a difference of, like we identified earlier, titanium, and the difference is copper is there, iron 2+ is there, zinc and titanium. Zinc and
Here,
titanium.
vanadium, chromium.
Yes. So here they have given, they're asking
Vanadium,
us
chromium.
vanadium and chromium, correct.
Chromium,
Vanadium and
copper,
chromium, which is a stronger reducing agent. Between these, they have not given the E0 values. They're expecting us how, what do you think would have been the right answer here? Now talking about this question paper, which is very closely related to what we are discussing about E0 values. Between chromium 2+ and Fe2+. This is, I think, a textbook question as well. I'm sure we're discussing E0 values.
Chromium 2+.
Chromium 2+.
I've gone as a textbook question, no, ma'am, which is a stronger reducing agent.
Correct.
Cr2+ or
It's an
Fe2+.
in-text question, ma'am. Chromium and iron, if you see, the Fe3+, Fe2+ is +0.77 from the data, and chromium, for chromium it is -0.41. Am I right? Yes.
Chromium -0.9.
-0.90.
M2+.
M2+ to M.
No, ma'am. When we say reducing agent, we look at 3+, 2+, no, ma'am.
Okay, yeah.
When we say reducing agent, it
Yeah,
gets
yeah,
oxidized.
Yes,
So we
right.
need to look at the second column only, not the first one. Am I right?
Yes, ma'am. Yes.
Yes. So we need to compare -0.41 and
Mine.
+0.77.
Yes.
But in this question paper, they have not given E naught values. So how do you help child understand? This is where sir asked, do we make them learn by heart the data? No, sir. We don't make them learn by heart the data. We only teach them how to interpret the data. So between the data, for the data given to us, I'm sure all of you will agree with me that minus 0.41 negative value, when the E naught value is negative, its oxidized form is more stable. When the E naught is negative, the oxidized form of that is more stable. So definitely Cr3 plus is more stable than Fe3 plus. So Cr2 plus is a stronger reducing agent than Fe2 plus. Are we have the same understanding on this?
And ma'am, this case, since the data is not given, how will the child interpret? Is there any other way, like we talk about T2G3 in the case of
Correct.
chromium 3
So
plus?
that's where I'm coming to, ma'am. Then
Yeah,
since
ma'am.
when E naught value is not given, what other data do we ask the child to rely on?
Yes.
What other data do we have? So that's where I said electronic configuration. So again, Sindhu ma'am, don't you think there is a little conflict here? Because when we say Cr3 plus enjoys T2 half-filled T2G configuration, whereas iron enjoys
D5.
half-filled D5 configuration. So again, the conflict is T2G3 more stable or D5 more stable? Child will definitely ask, why can't D5 be, why can't Fe3 plus be more stable than Cr3 plus? So how do you explain that? E naught value very clear says, at that point said, look at the textbook, E naught is minus for, but we can't rely on E naught. That's what the history has taught us. In the question paper, we are not given E naught values. So how do you explain that T2G3, half-filled T2G state is more stable than unsplit or degenerate D5 stability? Are others with us? I'm sure the other teachers are also part of this. Teachers, are you able to understand what we're talking about interpreting?
Yes,
Yes. So how do you explain T2G3 and 3D5, ma'am? Bhanumati ma'am. The child is going to say, we don't have E naught values. You
Yes.
say Cr3 plus enjoys T2G, half-filled T2G3 configuration. So it's more stable. So for Fe3 plus 3D5 is also stable only, no?
Yes.
Is this a question for all of us? How do you explain this to the child? Anybody? Any input? I'm only looking for little clarity here. It's not necessary how I say it or how I understood is to be correct.
Like minus value is more. That will undergo readily oxidation. That means
Correct, sir.
Fe plus 3. Fe plus 3 is Fe
Stable.
plus 2 to plus 3 is more possible if it is minus values.
Sir, here it is plus value, sir. Plus 0.77, sir. Plus 0.77, sir.
Okay. Okay. It will undergo reduction only, madam. That means Cr plus 2 and Cr plus 3. In that, only Cr plus 3 will become plus 2, but Cr plus 2 will not become plus 3.
No, sir.
That means
Cr2 plus will become Cr3 plus, sir, more readily. That's what the E naught value says, sir.
Reduction, madam, reduction means gaining electrons.
Sir, reducing
and,
agent, sir. Reducing agent means it itself gets oxidized, no, sir.
Yes, yeah, it's reducing agent means if it is having minus values, it will act as a reducing agent.
Correct, sir. That is, it's oxidized. Yeah, its oxidized state is more stable. That's how we ask them to interpret, isn't it, sir? When the E naught is negative, the oxidized state is more stable. In this case,
and in our board paper also, madam, Zn which is the strongest reducing agent asked. So I think so. I'm guessing that Zn plus 2 is. Am I right, madam?
Sir, there Zn2 plus is not given. At least in this set, Zn2 plus is not given, sir. The choice is B3 plus, Cr3 plus, Cu plus, and Fe2 plus. So here clearly it is discussing between Cr2 plus and Fe3 plus. Am I correct, teachers?
Yes, ma'am. For that particular set, that's the one.
That's the one. It's a discussion between Cr2 plus and Fe2 plus. So the answer is Cr2 plus only, sir. That is only stronger reducing agent. The data also proves that. The data also says
yes,
that
ma'am.
only, no, sir. Minus
Yes, madam, yes.
0.41 as against plus 0.77. So the data also points out chromium being stronger reducing agent than Fe2 plus, isn't it, sir?
Yes, madam. Okay.
So how,
Thank
where there is no data, sir, in the question paper, they have not given E0 values. So how will the child be expected to know without data that Cr2 plus, unless previous knowledge is there, this question cannot be answered. Do we agree?
Yes, ma'am.
Unless the child knows that
Value.
T2G chromium, when it becomes Cr2 plus, it loses one electron, becomes Cr3 plus electron. That Cr3 plus enjoys a half-filled T2G configuration, which is more stable in aqueous medium than 3D5 configuration.
So for manganese, we can interpret as T2G3 EG2.
Correct. No, ma'am, in
So
this
higher.
case, let us discuss this first and then go on to manganese.
Yes, ma'am.
In case of, why do you say T2G3, that's half filled? 3D5 is also half filled, no? For Fe3 plus, 3D5 is also half filled, isn't it, ma'am?
That's what I was telling, like T2G3 and EG2, the D5 split.
Okay, so you mean
So
to
you're
say,
having the 2 electrons in the higher EG orbital.
ma'am, Cr3 plus, ma'am, Cr3 plus electronic configuration would become
T2G3.
T2G3.
Yeah.
The 3 electrons in T2G.
In the case of Fe3 plus, it will be a T2G3 EG2. 5D electrons.
So we are having 2 electrons present in higher energy
orbital.
Yes, higher energy. And it also says, can we talk about CFSE, ma'am? Stabilization.
Yeah, ma'am, that's what. And
So
if it's aqueous solution, weak ligand, water can be considered as ligand.
Correct.
So the 2 electrons are moving into the EG.
Correct. In presence of aqueous medium, that is in presence of water, the degeneracy of the d orbital is lost. When degeneracy of d orbital is lost, then we have the orbital split up into 2 levels, and then the energy difference between them decides on where the electrons are going to be having lower energy. Hence, when we say chromium, the 3 electrons in lower energy when compared to the 5 electrons of iron in the split up or the broken up d orbitals. Is that how we explain to students when we talk about more stability of T2G3 than stability of T2G3 and EG2? So we don't compare T2G3 and 3D5.
Yeah.
We don't compare.
We cannot do that. Yes.
We should not do that. We should encourage them to see it as either CFC, if you take CFT and explain. And the tricky part here is we don't go to CFT earlier. We finish this chapter and then only go to coordination complexes. So at this point, it becomes mandatory. It becomes important for us to bring in the splitting.
Yes.
It is important. So somewhere during this discussion, we tend to digress. In fact, there are times when I end up drawing the 5D orbitals when I'm doing transition metals itself.
Yes, ma'am, always. Yes.
Yes.
We'll have to do that.
We have to do that. That is a very important takeaway today. What we are telling is saying that you have to bring in a little of CFT here at this point to make them understand. There is no point in make them learn by heart here and say at the end of the session, that is after their revision is over, when they go for the board exam, they'll know. No, you give them clarity here, it will be easier for them to pick it up from here. So that is one very important discussion on E0. And again, there is this wonderful question in our textbook also, where with oxidation states are given and they're asked us to compare the stability of the E0 values are given, 2 sets, metal 2 plus, metal 2 plus metal, metal 3 plus, metal 2 plus. So those E0 values are given, and from those E0 values, they are asked to predict the oxidation states. Predict the oxidation states. That is a very, and in that question also, that I'll tell you the question number that has compulsorily to be done in the class. You have to definitely do that question in the class. That is question number 8.17. Which data, the 100% you have to do that question. Child will get a lot of clarity on oxidation states and comparing it to E0 values. 8.17, where there are given 2 rows, which row to pick for which question. That also we need to tell them first. They will not be able to answer otherwise. And there's another question on give reason question, which is again based on E naught values. Wonderful question. Another of the favorite for board exam as well is 8.21. 8.21 is another favorite of the questions. 8.25, very, very important questions. Going on, I think we'll couple of questions more.
And also 11, ma'am. 8.11.
8.11.
All the reasoning questions very often.
8.11. Very, very important. Yes. Yes.
Madam, one small idea, madam, I got.
Yes, sir.
Madam, instead of standard electrode potential,
Yes, sir.
whether it is a reducing agent and all, when you are telling, when you see the electronic configuration as CR plus 2, only D4 electrons are there, D4. That means all are unpaired electrons. So it is easily can be removed. So that's what it is a very good, strong reducing agent. But in case of Fe plus 2, it will be 3d6. 3d6. One is one paired electron is there. One pair is there. So due
Okay,
to
sir.
the, in that way also we can compare, madam. I think so.
Sir, in fact, when you have paired electrons, interelectronic repulsions will make the loss of electron more easier.
Easier. Removal
Unstable.
becomes.
Losing that one electron leads to extra stability. So it will always tend to lose that.
So in fact, it will contradict what we are trying to say if you bring
Like
in that
when
point,
we
sir.
say nitrogen and oxygen, no, sir. Nitrogen and
Madam?
oxygen, the ionization enthalpy of nitrogen is higher than oxygen. Do we
Yes,
not bring
madam.
the same thing? No, sir. Oxygen has got 2p4. So in
Yes,
the
madam.
p subshell, you have got a paired electron. Removal of that paired
Yes,
electron becomes easier than removing the 3 unpaired electrons from the nitrogen. Half-filled electronic configuration stability, we say.
Yeah.
So,
Same, madam.
yeah.
Madam.
Yeah. Apart from
Thank you, madam.
attributing it to the half-filled, we also say interelectronic repulsion in oxygen makes the loss of electron easier. So it won't help, I think.
Okay.
So this is another
Okay.
tabular column that.
So I am
Fine.
also this thinking.
Sir, if we have gone into the
That is
process
actually
of thinking, sir, then we are this session is a success because we are not looking at exact answers which are not there always in the textbook. We need to find them out. We need to help children find them out. So if the session is able to at least trigger the possibility of looking at concepts, looking at tabular columns, looking at graphs in a different interpretation perspective, then I think we are heading towards better clarity. So let's go on to this tabular column. We have seen E naught values. This graph is also very famous. The observed value and calculated values, ma'am. Anybody would like to say how you present this in the class?
Yes, ma'am.
Please share how you present it to the class, sir. You can just tell us. The 3D series, sir. Only thing there is an anomaly when we compare the observed values and calculated values for cobalt and nickel.
All are having negative values only. That means that only except copper, madam. Copper only having positive value.
Correct.
So it will undergo only reduction. Remaining all are under.
It will resist oxidation. That's what you mean, correct, sir?
Yes, madam.
Right.
Yes.
Resist oxidation.
Remaining,
Go ahead, sir.
Remaining all elements will act as a good reducing agent.
We'll prefer to get oxidized.
Yes, will undergo oxidation.
Yes, sir. What about the blue and red indicators that they've given for cobalt?
Calculated values and
Yes,
calculated means according to formula when you substitute Nernst equation, maybe madam.
Yes,
it will
sir.
calculated value.
It's showing
But,
value little less than what it is actually.
Yes, ma'am.
So how do you explain this, sir? There's no explanation given for this. Ma'am, am I correct? Any other teachers present here can tell me. As a teacher, I was not able to identify any explanation given to this variation that is seen.
No, ma'am. In
textbook.
NCERT, there's no
And
explanation.
do we have any explanation for this?
No, ma'am.
Any of us?
NCERT gives no explanation, no, ma'am. It doesn't give.
It doesn't give, ma'am. It
No,
doesn't
no.
give. But
It's just
what?
the graph mentioning calculated and observed. Nowhere else any interpretation.
Nowhere else any interpretation. But this given for that only, isn't it?
Yes.
So I understand there must be some explanation for this. Anybody's come up with any explanations? Let's work on this. We'll meet tomorrow with an explanation. Try to find out explanation for this. So that will be an assignment for me as well. So we are together going to find out what is this anomaly that is because of, which is not given in the textbook, but this graph is clearly for that. That is the purpose of the graph. So this is very quickly, I'll run through the general characteristics. I'm sure you explain all this. In fact, in this year board exam, formation of complex compounds were asked. And I'm sure all of us are very clear when we say complex compound, what are the reasons, and catalytic properties, what are the reasons. We don't intermix this. They are not the same. Anybody share what are the reasons for complex compounds? Formation of complex compounds?
Variable oxidation state.
Complex compounds, variable oxidation states, ma'am.
And using
Small
that,
size, ma'am, small size. Polarizing power.
They can produce vacant d orbitals, ma'am. That's why they can accept.
Present of, sir, accepting is possible only when there are charge. Charge is high, isn't it, sir? When there is greater charge.
Yes, ma'am.
Right. Catalytic properties. Ability to form complexes is one of the reasons. Ability to form complex and multiple oxidation states here. Interstitial
and, providing active surfaces.
active surfaces. Right.
Yes.
Interstitial compounds and alloys. Interstitial compounds because of their
Vacant.
structural voids presence and
Vacant.
small elements like carbon, nitrogen occupying those voids. Alloy formation.
They can
Brass, bronze.
Similarity in size.
Nearly similar ionic radii. Nearly
No,
similar
no.
ionic radii. So formation of color and
Even melting
colored
point
ions
also,
and
madam.
melting
Even
points
alloy
also.
formation,
Correct, sir.
not
Melting
only
points
atomic
also.
radius,
Correct.
melting points and
Melting points
density. Density
True,
is also
true,
will be
true,
considered.
true. The core points, sir. The core point there. The core point, sir. And magnetic properties and formation of colored ions, we are attributed to unpaired electrons. And colored ions because of DD transition. Here itself we said DD transition.
Yes, ma'am.
That one aspect, ma'am, whenever we talk about color, always we have to refer to CFT theory, not the
Yes.
VV theory. Always.
Yes, always CFT
That
only.
should
When we're doing the coordination complex, again we'll touch on these, ma'am. And these structures we already know, and inner transition elements don't have to learn by heart. I normally encourage children to know the electronic configuration of cerium. The F0 is to begin with F0, F7 and F14 in case of lanthanoids. And in case of actinoids, we generally encourage them to learn definitely the electronic configuration F5F0, 5F7 and 5F14. The stabilities, and there's one question, europium +2 being a good reducing agent. It was there in one of the codes. Europium being +2 being good reducing agent. Europium,
Yes, ma'am. Yes.
though in this, if you see, europium 2+ enjoys 4F7 configuration. Europium +2 enjoys +4F7 configuration. But still it acts as a reducing agent. Did you catch that question in the board exam? Europium 2+ is a strong reducing agent. Europium 2+ is electronic configuration, as you can see in the slide, is 4F7. But still it is acting as a good reducing agent. What is the reason that we expected children to write?
Lanthanoid stable oxidation
Stable
status
oxidation
+3.
status +3. Hence, it acts as a good reducing agent, gets converted from +2 to +3. So, knowing this stability, the oxidation states and their electronic configuration again here forms the core of this. Not much here in this part. They have discussed more on lanthanoid contraction, its consequences. Mish metal, we have the discussion of similar properties. That's why we say properties of lanthanoid and actinoids are very similar. Very important point that is discussed is actinoid contraction being greater from element to element than lanthanoid contraction. That's one a very important aspect of this part. Apart from the variable oxidation state in actinoids, which is not so in lanthanoids, very limited oxidation states. So there's one very important question also in our textbook comparing the two series, lanthanoids and actinoids, based on electronic configuration oxidation states. Very important, electronic configuration oxidation states. So knowing this tabular column by heart is not necessary, but definitely the configurations, I would say, for in case of lanthanoids, generally cerium, europium, gadolinium, and lutetium. Very, very important for children to know these electronic configurations. And questions based on this is going to be based on electronic configurations. So no need to learn by heart. An assessment, we encourage, I normally do it, a rapid fire test, 5 minutes, entering into the class, give them 5 questions, 5 minutes on concept taught previously and give them the marks. Assignments, which we already do, class test, this is conventional routine. When we are going to go offline, we are going to give only offline class tests. And definitely go with revision before a terminal exam. Reflections are very, very important. The tests at 5 minutes or the 10 minutes test we give, we need to assess them and find out what are the learning gaps. That is a part of reflection. And see how much time was required for them to complete. When they are doing, they'll share this. I couldn't finish this part of the chapter. And how much time we took to complete a chapter. So this year or previous year, compare it with previous years. That gives us an idea about the generation itself, the kind of gaps they come with. So that forms a very important part of our teaching learning process, is identifying where are the gaps, where are the places that we missed.